Alright, so earlier on we looked at simplifying radicals, but specifically those were square roots. So the square root of 8, and we said that would become 4, not 4, the square root of 8 would become 2 radical 2. I'm going to show you two ways to do it, and I actually write it over here. It's 2 radical 2. And two ways to do it. And the first way we used to do is we would factor out a perfect square factor, and that would become 4 times 2, and that would simplify to be this. Another way to do it would be to factor out 3 factors of radical 2. That's just breaking 8 down as much as possible. And every 2 of them is 2, because the definition of the square root of 2 is a number when multiplied by itself is equal to 2. So these 2 become 2. Alright, so this is actually going to be the method we use most often when working with cubic roots. Alright, so this is a method that would work, and this is another method. So I would call this method perfect blank, either perfect squares or perfect cubes or perfect fourth roots, perfect nth roots. Let's call it that, perfect nth roots. And this method I would call prime factorization. Now, prime factorization is actually much more useful when working with nth roots, because we, as human beings, don't bother to memorize cubic roots, fourth roots, fifth roots, and so on. So let's take a look at another example. So let's say we wanted to take the cubic root of a number. So the cubic root of, I want to pick a number that's big enough that has a cubic root, or at least a cubic root factor. Let's say 400. Actually, let's do a number I definitely know has a cubic root. So 250. So if we wanted to take the cubic root of 250, we'll do it both ways. And one way will be with the perfect nth root. So we're looking for a perfect cube in this case. So the perfect cube that goes into 250 is 125, which I only remember because I've already done this video 6 times and had to reshoot it. So I've remembered it. I don't memorize my roots. So that would become the cubic root of 125 times the cubic root of 2, which would simplify to 5 cubic root of 2. Alright, so that would be the harder way, because you actually have to memorize your cubic roots, and I honestly don't know that many. I know 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, and 5 cubed is 125. After that, I have to use a calculator, so if I have to do it that way, I don't really want to memorize that many cubic roots. What if I needed a cubic root of 13? It wouldn't come to mind. I know the square root of 13. So let's look at this using a prime factorization method. 250 is equal to, now these are all in cube roots, but I'm just going to keep it simple for now. That would be 2 times 125, 2 times 125, that's 2 times 5 times 25, and that would break down further to 2 times 5 times 5 times 5. Alright, these are all cubic roots. Alright, just like these were all square roots. Now, the definition of a cubic root is a number when multiplied by itself 3 times will become the term in the radicand. So these 3 5s, because they're cubic roots, are equal to 5. And whatever we don't have 3 of can't escape the radicand. So 3 cubic roots of 5 become 5, leaving over a cubic root of 2. Alright, so let's look at a couple of examples. Alright, so we're going to use a prime factorization method to simplify 27x to the 11th y to the 6th. So 27 will break down to be 3 times 9, which becomes 3 times 3 times 3. X to the 11th is 11 x's. And 6 y's. And again, these are all square roots, so square root of this, square root of this, square root of this. I have to change color because I'm going to try and do this as fast as I can. So I just want to... Alright, I'm not even going to bother. I wouldn't do that normally, so I won't do it here. Oh, did my 6 y's vanish? I think they did. And are all 11 x's here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So, every 2 square roots of 3 become a 3. So that would be a 3. Every 2 square root of x become an x. So that's 5 x's. And every 2 square root of y's become a y, leaving us only with a 3x in the radical. Alright? Let's look at another example. Cubic root of 56 x to the 4th y. So that would be 56 is equal to 2 times 28, which is equal to 2 times 2 times 14, and that's 2 times 2 times 2 times 7. Alright, then we have 4 x's and 1 y. So, these 3 2's, these are 3 cubic root of 2's, which means 3 of them make a 2. We also have 3 x's, so 3 of them make an x, leaving us over with our radicand containing a 7x and a y. Alright, and just in case you didn't notice, there are some tips on taking the cubic root of a variable. That's actually much easier to do. If we wanted to take the square root of x to the 6th, that's just x to the 3rd. Alright, and the cubic root of x to the 6th is x squared. And if you notice there's a pattern here, you actually divide the exponent by the index. So the index here was 2, 6 divided by 2 is 3, 6 divided by 3 was 2. And the reason for that is there are 3 groups of 2 x's here, and there are 2 groups of 3 x's here. So let's just make up a random example. Let's say we had the, trying to use purple, doesn't seem to want to work. Right. Alright, there we go. So let's say we wanted to look at the 5th root of x to the 33rd, y to the 91st. I don't know, just making them up, doesn't matter. 5 goes into 30 6 times, so that's x to the 6th, and there are still 3 left over in the radical, and 5 goes into 90 18 times, so that's y to the 18th, with 2 left over, not 2, 1 left over in the radicand. So that would simplify to be this. Alright, so in short, to take a variable out of an exponent, divide its exponent by the index. I could write out 33 x's and 91 y's to show you that that'll work, but it's not worth the time. Let's look at one more example. Okay, like we just said, we can keep the a's into these easier. Every 3 a's is an a, so this will be a squared. Every 3 b's is a b, so that's b to the 3rd. And what is the prime factorization of negative 64? I know you can't take this, we haven't discussed taking the square root of a negative number yet, but the cubic root of negative numbers is possible, because if you multiply negative 1 times itself 3 times, you actually do get negative 1. So there are cubic roots that are negative. As a matter of fact, there are negatives for any odd root. There are no negatives for any even root, because an even amount of negatives will make a positive number. So let's factor negative 64 into its perfect cubes. Alright, so we need to factor into perfect cubes. So we're looking for 3. We might as well just factor out negative numbers. So that's negative 2 times 32. So negative 2 times negative 2 times negative 16. I'm trying to keep my numbers negative because I don't want to have a negative root in there at the end. Actually, we can do that. Let's do that. So let's just leave out the negative 1 to begin with. And that this is a perfect cube, so this will mean our answer is already going to be negative. Alright. So that's not radical, sorry. 64. So this we've already taken care of. A cubic root of a negative 1 will be negative. Are there any other... do we have 3 of the same factor? 3 because our index is 3. So that is 2 times 2 times 2 times 2 times 2 times 2. 64 is 2 to the 6th power. So every 3 of them comes out of the radical. So that's 2 times 2, which is 4. Alright, or we could have broken this down to be 4 times 4 times 4, which would also come out of the radical. So either way would work. Alright, so this is our simplified radical. Everything came out in this case. So I'm going to make up an example that's complex, just so we can make sure we understand this very well. Oh, I have one. I didn't even realize. Alright, oops, I have a lesson plan. Let's look at that later. So, fifth root means we have a negative 1 here. I'm going to assume we can, because it's a fifth root, we can just take the negative out, because there are odd roots. Every 5 a's comes out of the radical, so there's 1 a that comes out with 1 left over inside. 10 of these will come out and become 2 b's, leaving over just 2 inside. Alright. So let's worry about 243, which I don't know the factors of off the top of my head. Does 3 go into here? I don't know. 3 goes in here 8 times, 81. So this is 3 times 81, which is 3 times 3 times 27, which is 3 times 3 times 3 times 3 times 9, which is 3 times 3 times 3 times 3 times 3 times 3. So 5 of these makes a 3, because these are fifth roots. So this will become a 3, and there's 1 3 left over inside the radicand. So inside the radicand of our fifth root will be a 3, and a b squared. Alright, so that kind of covers, I think, enough examples to get across these ideas. Alright.